Welcome, everyone, to the workshop on possible futures. For those of you who've been here for a whole semester, I hope it's been a productive, fruitful semester and you feel entitled to have a good vacation at the end of the workshop or at the end of next week. For those of you who are here just for this workshop, a quick introduction to the Simons Institute. Simons Institute was founded in 2012 with the generous grant from the Simons Foundation. We focus on semester-long programs like the one this is part of, on modern paradigms and generalization, where the programs are on topics that have a strong theoretical computer science component, but not entirely restricted to theoretical computer science. We try to use that lens to look at other areas, including machine learning, very recently, and large language models, and so on. The program brings together, senior researchers and young postdoctoral fellow level people. Now you're wondering how we choose these topics for these programs. We want the community to propose interesting topics for programs. So if you have any great ideas for future programs that don't strongly overlap with programs we've had recently, especially, we are very open to that. So we try not to have the same topic repeat very, very soon after, with a short interval of time, but maybe after 7 or 8 years, we'd be open to a topic again. But if you have any proposals to make, we would really welcome that. I guess I want to thank Fanny and the other organizers of this workshop. And one housekeeping note, which I think I see everybody observing already, we don't allow food and drink in this auditorium. And congratulations. If you did bring food in this time because you didn't see the sign, it's okay, but don't bring it in for other sessions. Now hand off to Fanny.
Thanks, Sampath. We're excited to kick off the last workshop with all of you together of this fall semester Modern Paradigms Generalization. So when the organizers of this workshop, which is, Nati, Misha, both here, Serbi, not here polling, and Matus and I got together, kind of agreed very quickly that this workshop should be both retrospective and looking into the future and kind of speculative. And so that's how we came up with the name of this workshop, Unknown Futures of Generalization. And we wanted to have a program that has a lot of unknown and unusual formats. So in particular, I wanted to point you to 3 kind of less standardized formats. So one is going to be fireside chats for the retrospective part. We'll have 2 giants of statistics and learning theory, which is Peter Bickel, who is also in the audience, and Robert Shapiro later on, which is on Wednesday afternoon and Thursday morning. Then also we'll have a panel on Tuesday afternoon on the future of scientific research and education. And we'll have a debate. So we'll have a very structured debate format between Seb Bubek from OpenAI and Tom McCoy. So Sebastian Bubek wrote the papers Sparks of AGI, and McCoy wrote a discussion paper that was more skeptical called Embers of Autoregression. And so we have a debate called Sparks versus Embers. So the organizers spent a lot of time brainstorming about both the topics of the panel, the debate, and also the fireside chat. So we would really hope you could join us for these exciting activities. So besides these unusual formats, we'll also have unusual talks lined up. So besides the familiar faces in learning theory and statistics and TCS, theoretical computer science, we also invited prominent researchers in science that use machine learning techniques, also cognitive and neuroscientists, as well as developmental psychologists that will talk about learning for how humans learn, and humans and animals learn and reason. We'll also have representatives from 4 major LLM labs, Anthropic, OpenAI, XAI, and Google. And all of them have ties to the ML community. They used to have very important contributions to the core ML or theory community. And they'll be talking about their perspectives on LLM capabilities after joining these industry labs. So we're excited to have all these different perspectives present at this workshop. Now, before we go on to the first talk, just want to announce, in case this is not you haven't seen it in the schedule. So later in the afternoon polling, we'll give a talk that like the distinguished CARP lecture on robust statistics, I think, roughly, robustness. And yeah, hope you also join us for that lecture, which is 3:30 to 4:30. Okay, so now I hand over to Nati for the first session.
Okay, thanks. So we're happy to have as our first speaker, Florent Krzakala. So if you check, did I mispronounce it very badly? Okay, if you check Wikipedia, Wikipedia will tell you that Florent is a French mathematician. Those are lies. Florent is neither French, he's Corsican, nor a mathematician. I don't know where they got that. So Florent is a physicist by training, but has contributed a lot to theoretical computer science, working on the stochastic block model, on constraint satisfaction problems generically, and other, more recently on foundations of deep learning, and will speak to us today about how neural networks learns simple functions, still trying to prove us that maybe is French after all. Thanks, Florent.
Thank you. All right. Okay, it's great to be here. I just want to start by saying it's great to be back because I spent a fantastic semester here in the Simons Institute in 2016 with my wife and kids. We had the time of our life. I partied. I still had hair at the time, and it was great. And I went back to Café Strada this morning, and it's wonderful to be back in Berkeley. Okay, so Unknown Future of Generalizations, that's a very inspiring title, congrats for it. So I was thinking, what can I say about it? And, the best predictor of the future is the past, or maybe the present. And so I was thinking, okay, maybe I can speak of the unknown past and unknown present things that I don't get about generalization. And there are a lot of things we certainly don't understand, or I don't. And as Nati said, I'm a physicist by training, even though I'm not sure exactly what I am these days. I need to check who wrote this Wikipedia page. Certainly not a mathematician, but I do my best. But as a physicist, you are trained to simplify everything. Okay, if a physicist is doing biology, he or she will start by spherical cause in vacuum. Well, that's how you do. If you are doing material science, you see everything of harmonic springs, harmonic oscillators, which is essentially the only thing we can solve in physics. And of course, since we are discussing machine learning and statistics, well, we are discussing Gaussian data. Okay, so everything is super simple, but that's the philosophy. You try to see if you can understand simple settings. So maybe that will not give us AGI, but it will give us AGI, in the word of Jason Lee, which is artificial Gaussian intelligence. I really like this post. So let's try to reach AGI today. Okay, so I have 4 parts. Let's hope I can make it. So the discussion will be around that set of problems called multi-index functions. And what are those? So here is it. Okay, this is basically what I want to learn. This is my spherical cone vacuum, or my harmonic spring, if you want. You have data in d dimension. Let's call them x. And what I will do with vector, Gaussian vector, I will project them into r dimension. And r is finite. It's 1 or 2 or 7. And I project them with a matrix W, and all these directions are orthogonal. I'm trying to make this something very simple and to avoid the worst case analysis. And then what do? Well, I have r numbers, small r, and I use a function with these r numbers that output a label y. Okay, so this is called the multi-index function. Okay, you have x multiplied by w star, give you a vector with r numbers, and you do something, right? So example. Okay, the linear model. Just take x, I project it with a vector. I have one number, and I return this number. So simplest one. You can take the absolute value. That will be phase retrieval, or if you want, the real version of phase retrieval. Or you can take the sign and add some noise to make it more fun. Okay, and multi-index is an example. You can do something more complicated. Now you have like maybe 3 W star or a matrix which is D by 3. So now you have 3 value. You can have R, and you can do I don't know, a polynomial, a mix of all these stuff, more complicated polynomials, or even something that looks like a neural net. And the question is, okay, if you do this with n data point, you create a data set. Okay, so it's really artificial Gaussian intelligence. You have all these Gaussian data, and you have the labels coming from these functions. And I'm taking D to be large because I want to make computations. Can we learn this function from data? Okay, so if I'm giving you the data set, can we learn what was the function here? Okay, and obviously, can we learn them with a neural net? Ideally, a 2-layer neural net with P neuron, and P must be equal or larger to R in order to be expressive enough. Okay, so that's the setting. And many of us have been working in the setting over the last few years, or should I say decade. And so I'm trying to review a bit what we have learned. So the first thing you might try to do is to say, okay, look, life's too short. I'm not going to train my neural net. I'm going to keep my first layer fixed. This is called the random feature setting. Okay, you don't learn W, you train only the second layer. This is really easy to do. It's essentially linear regression because once you project here, this is linear regression on the so-called conjugate kernel. And it's a very popular setting because we like kernel methods. We can do billions of stuff. And there were billions of articles on this, especially once people realize that you can think of actual neural network in the Léger regime are doing something like this. But the bad news is that it's terrible. Okay, for such problem, this is giving terrible performances. There have been tons of work on it, but my favorite paper is this work by Songmei, Theodor Mizakevich, and Andrea Montanari. Songmei is right here in Berkeley. Basically say the following. If you have a neural network with n data point and the width is p, what you can learn is a polynomial approximation of your target of degree kappa, where kappa is the mean between the order of n and p. So if n and p both scale like d to the power kappa, or kappa 1 and kappa 2, you take the minimum one. So what this means is that if n and p, so if you have order d data point and maybe your neural network is has a width order d, you can learn only a linear approximation. So it's kind of terrible. If you have, n is scaling like d square and your width is like d square, well, then you can learn maybe the quadratic part. And if you go to the cubic, scaling, you can learn cubic scaling. So, for Gaussian data, all this stuff, lazy training and in general kernel methods, they are essentially polynomial fitting in disguise, at least once you look at this problem. Okay, I mean, there's nothing wrong with polynomial fitting, but it's hard to believe this is a summum of machine learning, though, depends who you ask. So the good news is that, a single gradient step can change completely the story. And there have been a lot of work on this. I learned this from this work from Ba et al. And also from the work from Alex, who's here. And just to show you how, just doing one step of gradient with enough data is enough to change everything. So this is an example taken from a recent paper of mine with my co-author, where we say, okay, look, we take order n data, or n equal order d data points. The target function is just sinus. We take a very large update. In fact, we take the largest step size that we could, and everything's changing. And it's very interesting. For instance, if you look at the spectrum of the covariance, it goes from the one you have for random initialization, which is the blue one, to something with fatter tail, which is the kind of thing you observe in deep learning, which are trained with more than one step, of course. And not only this, but you start to see a drastic improvement, at least for some problem over generalization. Suddenly, you go way beyond this limit of that you have with kernels. And you can even characterize what is going on. And so, just to give a heuristic argument, what happens? So what happens is that once your W hat, in your neural network, start to learn part of the hidden direction of the target, you have a massive improvement. So how to understand this intuitively? Well, essentially, this is what is going on, okay? So the part of the subspace that you learn, suddenly, you are not doing random features over the original data, but since you have learned the subspace, even with a bit of noise, you are now doing random features over this projected data, over the edges. And this is a low-dimensional thing, so of course, you get much, much better performances. Right? You went from a problem which is a high-dimensional one to a low-dimensional one. What happens for the set of directions that you have not learned? Well, essentially there you are still doing random feature in the original large enough dimension, and so you have these polynomial limits. Okay, so there is no generic proof that this is what is going on, but intuitively this is what is expected. And in some problems you can make precise rigorous statements which are more precise than this, but philosophically that's what is expected, and we should not be surprised. Obviously, we expect that if the neural network is learning the relevant direction, we should have a massive improvement. So the question I want to discuss is to focus on neural network and ask them, okay, can they do this? Or how hard is it for them to learn these directions? Okay, so this is really focusing on feature learning. So let's see if we can come out with a classification of easy and hard targets. Which functions are hard, which are easy, which are impossible, and so on and so forth. So let me take first my viewpoint, and then I will tie in with what our dear friends in computer science department are saying. First, let's look at a toy problem. Okay, something much simpler. Let's assume I actually know G star. Okay, so of course this is cheating, but let's type by cheating. And the question is, okay, now if I know G star, it should be easier because the only thing I have to learn are the directions. So how hard is it to learn the directions? Turns out, most of my Yoda masters in physics looked at this problem or some variation of it for the last 30 or 40 years. I'm just doing name dropping here. But they looked a lot to this problem. And there was some motivation coming from the work of Hopfield and et cetera. So after a while, we looked into this, and the bottom line is that order D sample are sufficient. Okay, and if you want a precise statement, I'm not leaving you with the physics prediction. We worked hard a few years ago, and we could prove entirely what they were saying. We have a tight characterization in terms of rigorous replica predictions, which is not what I want to say here, but essentially this is true. All right, we know exactly what is going on. We have proven for the single index, the multi-index, and we know what the best thing possible is. However, we don't care about what the best thing possible is. We want to know what the best thing possible with a good algorithm is, which is a harder question. Luckily, that was also something that was looked at first in physics, again motivated by Spengler's theory, but then it spread into mathematics, signal processing, and so on and so forth, especially due to the amazing work of Andrea here in Stanford. And long story short, the best algorithm that we know of for all this problem, and best in the sense that if you are just doing first order iteration, so you have the matrix, you multiply with the data and you iterate, the best thing to do, at least with order D data, is called approximate message passing, or in this case, the Bayes approximate message passing algorithm. I'm just writing what the algorithm is here. It's not that important what it is. I mean, this is your matrix of data, you apply it, you have something, then you have to do some Bayesian denoising, and then you apply it. It's an iterative denoising algorithm. The good news is that we can analyze what it does. All right, so what does it do? So we have a classification of problems according to what we believe is the best algorithm, or at least it's the best iterative algorithm. And essentially, we have three kinds of functions. Okay, almost all functions are what I call the trivial functions. That is essentially any, if you have order D data, you can learn this direction better than random with some different degree of precision, but you can learn them at least better than random. And this is what is happening for the vast majority of functions, okay? So, this algorithm is good, it's learning everything. However, there is a class which we call easy, the green class here, where it's a little bit more complicated. So what are the easy classes? So here is the point. To be part of the trivial part, what you need is that the probability of H star knowing Y should not be completely too difficult. So let's say that you have some Y's, you have some labels, and you try to see, okay, what is the posterior probability over Y, over H given Y. So usually this is something which, I don't know, can be something, okay? But if for any Y, this thing has a zero mean, then the problem is in the easy category, not the trivial one. And this can only happen if you have symmetries, essentially. For instance, if you have this problem, well, if I'm giving you Y, well, you know what H is. It's either plus or minus square root of Y. So an average is 0. So this condition here is not satisfied. And in general, when you have symmetries, you will always be in this situation. But you need at least a critical number of data. So you have an alpha C, n over d should be larger than the constant. And then you can learn. So alpha C is 1/2 for phase retrieval. And if you have two directions, you have a more complicated formula. I'm just giving to you. For instance, sine of H1 star and H2 star, you have a transition at pi 2/4, and then you can learn. And finally, you have the nasty problem, which we call the hard one. If alpha star, this formula happens to give you infinity, then it means you cannot learn with any ordered data, at least with the algorithm. So these are the hard one. It's hard to create them, but you can think of parity with more than 3 directions, or 3 or more directions. Or if you are very creative, like Alex, you can invent some. But parity is essentially the one you should keep in mind. Okay, so we looked at this, we were super happy, and then we knock on the door of computer scientists, which means actually talk to Alex. And he said, oh yeah, we agree, and we talked to a bunch of people, say, yeah, sure, but that's what we find too. And if you look at the so-called SQ bounds, statistical queries, and I'm mentioning SQs, but there are also similar results for other complexity classes. Essentially, they found the same thing. It's harder to be completely generic with multi-indexes, but morally, this is the same thing. There is this classification with so-called generative exponent. They have the trivial problem. They have the easy one. They call this generative exponent 1, generative exponent 2. And then they have, subdivisions here. But for me, they're all hard. So I will not consider that. So, it's great. We all agree. We know which are the easy and which are the hard ones. Okay. And as a physicist, I'm really happy that, everything is easy unless you have symmetries, because then, you have to break the symmetry somehow. So it makes sense that somehow it's slightly harder. Yes. Yeah, but R is finite in everything I'm saying. So I didn't compute. Now, if you start to have R that grow, then indeed, it will be interesting. Then you have to look into it. And I avoided it. But keep this in mind, because at some point I'm going to come back on this. But let's say that there is some order R in prefactors. Obviously, in this formula, implicitly, if you go back one slide, like here, I have to compute the soup over P by P matrices. And P is actually R. So, some things are hidden there. And it's a very interesting question, what happens where R grows. I agree. Right, but I will think R 1, 2, 3. More than 3 is infinity for a physicist. Log of infinity is basically 6. Or maybe 7 with double precision. Okay, just to show you that it works, this is sine of H1, H2. And that's what we get with the algorithm. That's what is predicted by the theory. You have this nice phase transition at pi square over 2. And I need to mention that this is something quite cool. The only subtlety with multi-indices is that you can learn something, and then something else can become easy because you have learned the first thing. For instance, here h1 squared is not so hard. You should learn it if alpha is larger than 1/2, and indeed you learn it. But now that you know h1, this is not parity with 3 directions anymore. It becomes parity with 2 directions, which becomes something doable. And indeed, well, after a while, you start to learn this thing. Okay, so you have this interesting, iterative learning. It's something that was pointed out by Emmanuel Abbé and collaborators, Theo and Rick. Even though here it's a slightly different class, I will come back on this. So we call this class a grand staircase mechanism. And a grand staircase is different from their staircase, and I will come back on this. So this is a grand staircase of Titanic, for those who remember the movie. So cool, fine. So everything is easy. We have these 3 classes. We have the staircase, well, the grand staircase. Everything is nice. But of course, this is cheating. Nobody cares about this. Nobody run AMP. Nobody knows this algorithm. And you don't even know the function G in general. So that's not what we want to know. So what we want to know instead is, if I run all this with a neural network, will it be as efficient? And will the neural network learn all this direction with that many data, or will it be really terrible and need much more data? That is an interesting question. Okay, again, we maybe don't really fully understand machine learning in general, but with Gaussian data, we are really good. We are really good at artificial Gaussian intelligence. And even gradient descent is something that, we have a good understanding of what's going on in asymptotically with Gaussian data. Here is a review, it's probably not complete, of many works that looked at the situation where you are doing 1 sample at a time. Okay, so you give me 1 sample, I'm doing 1 step of gradient descent, I throw away the sample, and so on and so forth. Right? This is a very popular setting even in reality now, because there are many systems that we train like this. But for theoreticians, it's great because you have less memory and you can try to prove theorems. And so let's try to see what's going on there. So instead of going through all this work, I will give you what is going on with a very short argument. So that's the only computation I do here. So here is what's going on in a nutshell. So if you do spherical gradient descent, I'm doing spherical gradient descent because it's simpler. Your update is something like this. This is a gradient. And because in spherical, the gradient is orthogonal to the weight, you can simplify it to something that looks like this. And the only thing we want to know is, does this correlate with the target function? Okay, so let's take the target function with only 1 direction to understand what's going on. So I multiply it with W star on both sides. And essentially what you see, that M, my correlation at time t plus 1, is obeying that kind of iteration. All right. Now, obviously, if you are a physicist like me, you forget completely of the math and you don't pay attention to the detail. Of course, if you want to write the paper, there are a lot of difficulties here. But come on, I mean, I'm putting this one on this side. Clearly, what happens between 2 steps, if I have a lot of data, is that I can replace that by its expectation. So I expect to have my correlation to obey a differential equation like this one. Okay. Now we can write what the gradient is. The gradient looks like this. Okay, this is a true function. This is a derivative of your activation. So you look at this in the eyes. You have expectation over Gaussian data, but you see that this depends only on these projections. So you introduce these 2 numbers, h and h star. H star is the true projection. H is the projection in your system. They are Gaussian data. So again, they depend only over M, which is a correlation between W and W star. So you can perform this integral, this high-dimensional integral. It's just a 2 by 2, it's just a 2-dimensional Gaussian integral. In fact, you can simplify this by integration by part. And since these are Gaussian data, it's natural to expand that on the Hermite basis. Okay, and you expand that on the Hermite basis, but then the expectation is super easy to do because there is a beautiful thing with Hermite that the expectation of two different random variable is 0 unless k is the same on both sides, and in which case then the expectation is just a correlation. So that thing is just given by this expansion. And if you assume now that we are close to initialization, m is very small, so we care only about the first non-zero exponent. So if you call L the first non-zero exponent of the target function in the Hermite basis, because I had this derivative, you will see that the first non-zero one actually, m is going to L to power minus 1. Okay, that's all. That's, if you forget the fancy math, which is kind of interesting actually, because you have to control the noise term, the error, and martingale, blah blah blah. That's what you got. That's indeed what is going on. And if you analyze m and you start from close to 0, you will see, well, it all depends on this exponent. Okay, so this is essentially what was shown by Gérard Benarous and collaborator, a little bit more cleanly than that. And they basically say, look, if you expand your teacher or your target function into polynomials or Hermite polynomials, and you look at the first non-zero one, call this L, we call this information exponent, well, if the information exponent is 1, you need order d data. If it is 2, you need d log d. And if it is 3, you need d square. And if it is 4, you need d to the cube, and so on and so forth. Okay, it's very nice result. But it's terrible news. This is terrible. Because this is telling us LGD really sucks. It's really, really bad, right? We went from AMP, which of course was cheating, but was solving everything ever with D or alpha D. Okay, here you have to run it D log this, log this time, but I mean everything was easy except those. To something in which now, if you have something which is to the power 4, suddenly it's super hard. And so taken at face value, this is telling us that neural networks should not work. They are really bad, and at least for some of these functions they are bad. And if you look, the multi-direction case, not much change. That's not true, but morally, you have to look all these directions, all of them have their own exponent. And so if something appears to the power 4, minus blah, blah, has to have the Hermite coefficient, it should be d cube data. So that was investigated a lot in full detail by this work by Abe, Boadatsera, and Misakevich. And they also found that there is a staircase mechanism. Actually, they invented this concept in this paper. But the staircase is different. Okay, so the staircase is in terms of its Hermite coefficients. So for instance, if you have a function like this one, you see that here you have something which is essentially quadratic, so it will take a lot of time, and this is also something which is hard. But luckily, you first learn H1, then knowing H1, well, H2 is linear, so you can learn H2. But if you know H2, then you learn H3. So they have this beautiful iterative learning of direction, which they call the staircase. But it's not the same staircase as before. It's the staircase between these weird Hermite constructions. So, these are beautiful results, but somehow they are telling us that there is something inherently bad about gradient descent, which I refuse to believe. Okay, so here is the question. Is it true that neural net trained with GD are that bad? And the answer is no, because right here we did just online learning, or we used just the square loss. Nati will solve this slightly differently. And we were lazy. We were trying to follow rigorous math, and it's okay. It's easier to do theorems with fresh sample each time. But what if we repeat gradient descent with a fixed box instead, right? And like I take my big data, I'm taking a big vector, I'm doing 2-step. And then we find out that it's completely different. Okay, so for instance, here we just do 2-step or 6-step of gradient descent with one big batch. The batch is order D. Hyperbolic tangent at information exponent 1. So if we change the batch every time randomly, we follow, we learn, but that's we knew. But if we keep the same batch we learn. It's not as good, but we still learn. But if you take this function, which is Hermite to the third Hermite coefficient, essentially h3 minus 3h. Yes, I think this is this. You don't learn anything in any finite time. But if you use gradient descent and you repeat over the same batch, after 2 iterations, then you learn. And we could prove this, actually. We could prove the following. After 2 iterations, anything which is in this class can be recovered. So that's encouraging, okay? Because that's entire trivial class. We could not prove the following, but I believe it's true. If you do order D batch size and you iterate log D time, and if alpha is large enough, I believe you will learn this entire class as well. That's what we see in simulation, but we cannot prove this. So what can we prove? So there is a simplified setting where we can get very nice results, which we consider recently. And there was essentially the same idea developed by Jason Lee collaborator for the single index case, which is okay. Maybe what I should not do is something that complicated, which is having a full batch. But maybe the important point was to have repetition of data. Okay, and repetition of data is something which is always there. Like if you look at a data set, you have a lot of duplicates in the same data set or near duplicate. It's like this. Even if you consider LLMs trained, with one pass, come on, the same sentence is repeated billions of times. Okay, so from time to time, you are iterating twice over the same data point, essentially. Okay, and in fact, there are even algorithms which are especially literally doing this extra gradient algorithm, which every time you give them one data point, they do 2 steps onto this one data point before moving on. So we looked at what happened if you do stochastic gradient descent online, but instead of doing 1 step, we do 2 steps, and then we throw away the data. And it turns out, long story short, that is enough to have SGD working for this function class. You can learn the Hermite 3 in linear time. This is Hermite 4, so it has a symmetry. I cannot learn in linear time. I need D log D, but you see it works. While the normal SGD without repetition is completely failing. Okay, so what can be proven here? So essentially, we can prove that for target without symmetry, you can learn with order D data. With target with symmetries, you can prove you can learn them with D log D, at least for single index. The proof seems to be more complicated for multi-indices. So, I have no doubt that it is true, but it's still something open. And we actually believe that you can learn parity with a time D to the R minus 1. That is also open. You can of course simulate it and see that it's true, but that's not how math works. But the good news is gradient descent works, which maybe is not so surprising. And so why? So what's changed? So let's go back to this argument. So you remember what we did here when we look at SGD. Well, how does it change? Well, the only change is that we don't have the weights at time t here, but the weight at time t minus 1, because we did 2 iterations. Okay, so this WT is WT minus gamma gradient at the previous time. And if you expand now everything, well, you get a more complicated formula. And what is important is that the labels, they don't appear here linearly, but you have basically a combination of many powers of the label. And that is really important, because that was precisely the distinction between the 2 classes of algorithm. Okay, so the correlation statistical queries class that was characterizing SGD was the class where you are basically computing expectation of linear. You can do whatever on the data, but it has to be linear on the label. And so maybe it's not so surprising that this is what is, that kind of thing is what limits gradient descent in the setting. However, when you do twice, you are doing crazy transformation of the label. So you are into intuitively to the SQ class, and this is why you have this change. Okay, just to illustrate that change, you go from the staircase picture to the grand staircase picture. So for instance, some problem like this, which is h1 squared plus sine of h1, h2, h3, you can learn in d log d steps with both approach, right? Because that needs d log d anyway. And then knowing one, here you have something which is also d log d. So that will be learned without problem, but with both algorithms. However, an example like this one is not a staircase in the sense of my friends, because I mean, it is a staircase, but not with the same complexity, because here I have the Hermite 4, so I will need d to the 3 data to learn this, and then I will learn that. But with repetition, instead of d to the 3, I still need d log d. And, this is what you can see here. Okay, so yes, right? I mean, you have to tweak a bit things, but 2-layer net are good. Maybe you are not so surprised, and this is good. But somehow, this is nice. But then it basically says these functions are too easy. Okay, so we need to look at more complicated function if we want to probe things about deep learning and the advantage of depth. Okay, so the last thing I want to discuss is a recent set of works that we are currently writing, which go beyond a multi-indices model, and where we try to see what we can say about the advantage of depth. Okay, so this is heavily inspired by this work and by conversation with Alex, so all credit due, but with key changes. Okay, so now I'm looking to more complicated targets. Here is what I do. I have my data X, okay, and I still project them, but now I project them not on R finite, but square root of D dimension. Huge amount of projections. Okay, so I have all these projections, Z1, Z2, to ZR. So maybe I have 4 of them. Sorry, but yeah, this number are wrong. But I have square root of D of them. So this is a D here. So so I'm doing this, and then what I'm doing here is that these Z's, I'm applying a polynomial on them. Okay, so each of these Z is living in square root of D dimension. I have R of them. And I'm applying a polynomial transformation. Okay, I'm still in D dimension. Then I'm projecting them back to 1 dimension. And so now I am back to a multi-layer, a multi-index model with only R directions. But these directions are coupled in a much more complicated way with my origin. Right, so now if I try to learn this with a 3-layer network, what's going on? Okay, I'm going to briefly review 3 scenarios. The first one is, okay, no feature learning. Okay, so W1, W2 are random. I'm just training the last layer. The number of data points is D to the kappa, and kappa can go from 0 to 2. So what do we expect? Well, I mean, this is essentially a random feature model. Okay, so it's equivalent to something like this. It's a random feature in D dimension. What should we expect? Well, if n is not even linear in D, no learning. And then if n is n is going more than linear up to D squared, you can learn the linear part only. But in my example here, my polynomial was squared plus cubed, so there is no linear part, so you cannot learn anything. Okay, tough luck. Scenario 2, you train first the first layer and then the last layer. Okay, and now I'm training the first layer with a lot of data. How many? Well, let's see. These Z's are living in square root of D dimensions, because these are projecting to square root of D dimensions. And each of them is living in dimension 2. So you expect that you have square root of D times D parameter. And so if n is larger than this, maybe your W1 hat will correlate with this W1 star. Which means now what you should be observing is something which is not doing operating on X, but directly operating on the Z's. So naively, it's okay, fine. Now your model is doing random feature in reduced dimension, is not in dimension D, but dimension square root of D. Okay, is it better? Well, yes, because this is something that starts to happen when kappa is 3/2, which means now you can express with random features, well, whatever it is, that you have. And since your effective dimension is square root of D, well, D to the 3/2 is square root of D to the power 3, so you can fit cubic terms. So you can approximate this function up to cubic. Okay, and now let's say that you learn all layers. So you first learn the first one, so you reduce this to this star. Then you learn this one. And again, if you do some counting, you realize that you need, again, D to the 3/2. Now it's great, because now you have essentially random feature on these H's, which are finite. Which means now you are doing random feature over a finite number, and you expect that you can fit perfectly any function. Okay, so this is a lot of expectation, but it works. This is a simulation. So here I'm changing kappa. So kappa is log n over log d. Scenario 1, which is completely random. There is no learning whatsoever. Just straight line. Scenario 2, I start to have something good. In fact, scenario 2, you can show that you can expect that it goes to what the best two-layer network will do with as much data. And increasing the size, you see you go closer and closer. And indeed, the behavior change when kappa is 1/2. And scenario 3, when you learn everything, well, you go beyond what you can learn with two-layer net, and again at the same place. So it seems to work. And indeed, we can prove partially this with a few cheats because it's hard to do math. But essentially, we can show that in this scenario, we have an advantage of training a 3-layer over a 2-layer, exactly with that kind of dimensionality reduction that comes. Okay, and so I think this is a cool result that we're writing now, and it's an adaptation of some work of Alex, and also using some techniques by Songmei and Theodore and Andrea. Okay, I'm done. I think I'm.
We have 2 minutes.
2 minutes. Okay, so I can read my bullet point, right? So the first thing I wanted to show, at least for artificial Gaussian intelligence, we certainly reach it for a multi-index function with 2 LLM. There are still some open math questions which are really interesting, but I don't think that we doubt that this is true. There is this cool fact that you have iterative learning. There is this beautiful staircase picture of Abe et al. Which is actually even more powerful than previously believed once you repeat data. And these are a bit too simple to consider deep learning. But once you move to these multi-index 3 and multi-layer 3-index function, then you actually reach situation where you can prove for some scenario the advantage of multi-layer networks over 2-layer ones. Okay. Now, of course, all of this is, artificial Gaussian intelligence, and even this is an overstatement because, you can do more interesting stuff. What happens, if you do mixture of Gaussians, if you have token data, what about doing some real architecture? And that's the kind of thing that, many of us are currently doing. So I will stop here, and let me just take the opportunity to thank everyone who was involved in this work. And, there are certainly most of them on this picture taken in Corsica. Okay, thank you. Thank you, everyone. I hope I'm on time.
So we have some time for questions.
Single index model. So for single indexes, so you mentioned there's still kind of a gap between what we can do and what is known.
I think for the single model, we are very close to everything. So there are still various gaps. It depends. For instance, if you just say, like I do, oh, I want to be able to do weak recovery on the subspace, I mean, that's pretty much understood. If you want to be saying, no, I want guarantee on the generalization error, well, that's harder. Most results are, they are assuming some particular form on the activation function, that kind of thing, and that's not. Yeah.
I thought that it's like the gap.
Yes, and okay. So this gap is also, especially in for multi-indices. Okay, so so there are two cases, right? One is one big step of gradient that you iterate. So this one, there are a lot of gaps. Let me go back to my claim. Okay, here it is. So if you have a giant, not giant, let's say, a batch of data which is order n, we expect that all these things with symmetries, if you have enough data, which enough is not clear how much it is, by the way, and you iterate it log d times, you are going to learn all these things with symmetries. Okay, so we don't know how to show this, and something else that I don't know is how alpha should be bigger than alpha c. And for instance, is it just enough that alpha is equal to alpha c? Maybe, maybe not. And if yes, it's probably you need really p to be very, very large. All this is not really completely, it's not really understood.
Instead of log d steps, can you do log d units? Is that enough?
Log d step. Well, it's log d step, but the batch is.
Log d steps. Do log d units. This is constant units, right?
I think it should be enough, but certainly not to reach alpha c. Right? I think that what should happen is that the critical alpha that you have will be really large if you have only log d unit, maybe smaller over d and over d square, and hopefully if you have an infinite number of p's. It's like, I mean, of course, if you pre-process the data, you can do everything, and you can, we know how to do the stuff. The question is, the pre-processing done by gradient descent, is it actually reaching the stuff? And, I don't know. I must say also that, the techniques we use to prove this result is DMFT, which is something that comes from physics, and that was later proven, by many people. And it's really hard to use it in the setting, but there are a lot of smart people looking into this. Now, if you are looking to the second algorithm, which was HGD with repetition of 2 steps, so there is this beautiful work here that basically says everything there is to say in the single index, and we are trying to do multi-indices. Here is what I believe. That thing should be okay in D log D with this algorithm, we are getting there, but it's multi-indices are hard. And something which is even harder to have a rigorous control is that case, right? So this is clear that it works like this. Like once you learn a direction, you are starting to learn the other one. But to have a rigorous control on this, it's really annoying because you should basically start to say, haha, but now I'm learning this one. Maybe it will perturb this one, and it's really a mess. So as a physicist, what I did, since I have ODE in 3 dimensions, I just integrate it. So I know it works. You can do some various cheat, like, oh, once I learn something, I freeze it, that kind of stuff. But come on, we should be able to show us. So yeah, there are various things which are open.
So the grand staircase, I understand the high level, but is this, do you have a specific characterization of what can be done this way, or is this just a good picture?
Yes.
But and can it generalize beyond just do you have a sense of how it generalizes to, I mean, taking the staircase idea as the process that's going on in neural networks in general, which I think.
So take the staircase ID and replace the informative exponent with generative exponent, and basically that's what it is.
But taking this beyond just the multi-index model to what can be.
Well, yeah, I mean that we're only starting, but yeah, I think that is an important question. So Lenka is writing something on transformer using this idea. So stay tuned.
You started by talking about the artificial Gaussian intelligence, and how much.
Well, I royalty all due to Jason.
But how much are we missing by just focusing too much, or if we focus too much, or focus just on Gaussian data and squared loss and everything squared and these simple models, and I think what you said, symmetries are kind of really change things. These are things with a lot of symmetries, right? Are we getting, do you think we're getting, does this actually paint us the right picture, or is there a risk that we're actually getting completely the wrong picture by focusing?
That sounds like a panel discussion. So let me say, I think that, for instance, no, this is a great question. So for instance, I think this thing that we see here, that we have to do all this clever cheating to go to the grand staircase, and I think this is just due because we are looking Gaussian data. It's a very fragile behavior, right? And I think the correct picture is basically this one. Like, look, either a function is easy, you learn it. There are symmetries, you need to break them, or the function is super hard, like parity, and you don't learn. And that sounds like what we should have found at the first place. The reason why we had all these weird cancellation with Hermite coefficients is really because it was, purely Gaussian. And in fact, like the only thing that happens when you repeat twice is that you're perturbating the Gaussians. So as much as I want to defend, the idea of looking Gaussians, I have many works on Gaussian universality, or, everything is Gaussian anyway and everything. Well, we should remember that it is, as our friends in statistical learning theory likes to remind us, there is still some danger into looking too narrowly to some data class.
Okay, let's thank Florent.
Thank you.
Break.